Hello everyone, welcome to the Easy Power Tuesday Refresher webinar series. My name is Jim Chastain. I'm an Applications and Solutions Engineer at Bentley. And I say as we start that this is one of the more fun presentations that I get to do. I hope you'll agree by the time we get through with it. And as we're in the habit of doing, I like to start with a couple poll questions just to let everyone get settled. First question is, how often do you use impact motor start? I want to be comparing the two. Impact motor start is a feature of EasyPower PowerFlow, and some people have never heard of it. Some people don't use PowerFlow. Some people would if they knew more about it. So, okay, looks like we're there. Here's how people have weighed in. So, strangely, isometric distribution. Good, thank you. Then the second question is, how often are you concerned about dropping out large loads or any loads when you start a large motor load in your system? And this is something that comes up, especially when you have things like high volume air evacuation or large pumps. And sometimes you want to prevent having everything trip offline because you turn a large motor on. And just as forewarning, that's one of the primary reasons for transient motor start. So it looks like we have a quorum. So it looks like we're in agreement here. That is, it's at least something you want to be aware of. Thank you for participating. Well, transient motor start is based on PowerFlow, but the thing that separates impact motor start from transient motor start is the calculation method. Impact motor start is an instantaneous check in time where the tool will calculate basic power flow using the basic current injection methodology, but it does so at the worst case across the line start point where we have a locked rotor draw on the system, and so the impedance is based upon the starting MVA and the power factor that the manufacturer, the typical value that a motor manufacturer will have for power start. But it does show the potential impact in an extreme situation, and I'm going to try to relate that to what we see on the TCC curves. So let me jump into EasyPower. So I want to make a point that this example is in your installation under the sample folder, and if you have PowerFlow, you can do this analysis yourself. But what it amounts to is we have two very large motors down here on a 4.16 kV bus. When I go into PowerFlow, the tool will solve based upon both motors being online, and everything's designed to accommodate that with nominal voltage drop. Now, I want to mention the same example can be used for dynamic stability. The difference between transient motor start and dynamic stability is the inclusion of generator models. So for transient motor start, this will not be populated. But in PowerFlow, I can say, well, what happens to the system if I have one motor online and I bring the other one to start the other one? Well, I can open and close the breaker, but because I have PowerFlow solution at quiescence, it's not going to capture that transient effect or the impact effect. So I'm going to put it back online and change the temporary motor data dialog to start at 0% rather than 100%, and then allow it to be start in the impact motor start mode. So based upon the horsepower and the power factor and the locked rotor multipliers of the full load current, we'll get, with the system offline, need to indicate that it's motor starting. Okay, so now it's offline. We're at quiescence and power flow. We're drawing 360 amps. If I do an impact motor start with this little icon up here on the top row on the left side, it again calculates the instant I apply the load across the line with that very low power factor. And you can see the current is 10 times what normal current was for a single load. And what the red indicates is, so we're in the power factor mode, we're showing the voltage violations and the overloads. We're showing for that particular instant, we're overloading the transformer by 119%. We've got our bus voltage drop down at 0.78 per unit compared to the 0.96, I think it was, and nominal. Now, the question is, the fact is it'll never actually reach this condition as long as the motor starts. And so just out of curiosity, you might say, well, does this particular starting mode cause damage? If I go back to coordination and I look at my motor starting curve, so I was looking at 32, I think it was 3,200 amps. Let's go ahead and, I'm winging it. I probably should have gone back and I'm going to insert a tick mark. I think it was 2,200. So that transient motor start current will last for less than a cycle, instantaneous. It will not cause damage to the motor. This is still in the normal motor start range for the motor starting curve. And we can see that only if that current lasts 4 or 5 seconds does it really start to get up into the point where it's an abnormal starting curve, abnormal starting current. So it doesn't prove anything, but it shows that my protective devices won't be activated just during that instant of doing the impact motor start. Okay, so that's the function that's built into power flow, normal operations. So now we want to compare that to transient motor start, which takes into account still a power flow calculation, but the dynamic modeling of full flux models, including full flux models. And to do that, in my database, I go into my, so that was the impact motor start. We're going to show an example where we're going to be using simulation using the full flux power model, motor models. It's based on power flow, and the results will be more accurate because it's going to accommodate the changes in the system. And so I've included in the handout the dynamic tutorial that includes motor start and the sample file that I'm using if anybody should want to try it out. You need the demo tools or at least access to the transient motor start module. But as I say, this is built into your system, so if you go look into the tutorials under power flow analysis, it'll go through this example. So we're going to modify the motors to include the full flux model. We're going to digitize the store, or we could do the same modeling if we digitize this torque and speed curve, show how that's done. We're going to run the simulation of one motor start and then plot the effect of the, showing the effect on other motors in the system, and then how soft start can be simulated. So we're going to try to accomplish all that in one fell swoop. So I'm back in database edit. I'm going to open the model for the motor itself. Now every element that can participate in dynamic stability has a tab called stability in its setup. And for motors, we need to activate the motor model. And then we have a choice of doing a generic, a plug-in, a Rockwell, or a Siemens. Rockwell and Siemens are significant library additions that we have, and it's worth kind of going through the part numbers to see what matches up with what you're using. I'm going to use generic for a standard induction motor, and I'm going to bring in all those parameters, including transients and subtransients and time constants. And it's going to ask me if I want to overwrite the power factor and efficiency. If I don't, then it's going to model a generic version of the size of motor that I'm using. And then for the motor starting load, I'm going to use T versus speed. And likewise for motor running, generic T versus speed. Now I mentioned if we don't have the part number, or if you have access to the torque speed curve, you can use the digitizer to simulate the loading response, and I'm not going to do that now. Let me see if I can find it. I've lost the example that I used. The point is, if I have the torque speed curve, I can digitize against the model image, and it will fill in the parameters that can be imported then into the flux model this tool is using. But for now, I'm just going to use the standard values. I'm going to click OK. And you see that the icon for the motor now has a rotor image. I'm going to right click and copy and take that same information over to the second motor. Now when I go into to stability, the tool resolves the quiescent point, a stable quiescent point, with the motors online. Now if I take one of these motors offline, open and resolve with this breaker, this shows me the current state using power flow calculations. This frame is going to show me the plot of whatever parameters I want to monitor, and then this log will tell me the timestamp activity that happens in the model. So I'm going to click on this, double click on this breaker to put this motor online, and as I do, it goes through a 6-second simulation where we spend 1 second at quiescence. We turn on the breaker, and then we're plotting the motor voltage, the motor current, the motor speed, and then the motor torque for motor 2. So we see the voltage applied, we see the current. I didn't want to do that. Bring that online again. The tool knows that we're interested in the current and the voltage in this particular load. And so we see the voltage, the current, the speed, and the torque. Now you might say, well, what does the effect have on this other motor? Well, let's reset. Let's set up a plot. And now, well, this is if I were to do a fault. I want to look at the current through M1. So monitor let's go ahead and do the bus voltage on MCC 416. Let's do the motor current in M1. And per unit. And then let's do the speed of motor M1. So I want to do this as I activate or bring that single line motor online. So I'm going to bring this motor online. The auto plot is going to show me the current for this particular load, and then my defined plot on plot 2 is going to show me what happens on the motor that's currently online. So this is what we saw for motor 1, motor 2, and if we go to plot 2, this is what we see for motor 1. In the worst case, we see the voltage drop to a 0.8, the current drop, and then recover from a 0.3 up to a high of 0.48. And then my speed just didn't hardly do more than a glitch. So the question then becomes, well, what if I want to plot this? I can highlight the spreadsheet. I can do an Control C. I can go into Excel. Put it in here. And then in Home, I can insert a plot. I need to thin out the density of, the point is I can manipulate it in Excel. But I've got too many. I need to thin out the number of samples I'm taking. Calculations are being made at every half cycle, so it's extending my copy capabilities. Okay, so now let's say I want to see what happens if I do or impress upon the starting motor a soft start capability. So let's go back to database edit. Let's go ahead and save everything. Open up the dialog box for M2. Look under the stability tab. And now, let's say for soft start, rather than going to 100% across the line, let's say initially we go to 25% and then to 70%. We stay in each condition for 1 second, just winging it. So I set the time to switch at 1 second. And so we'll see a different curve now based upon it having the motor start with a soft start. Again, I'm just winging this. This is not the way you probably need to do it, but trying to show the merit of the capabilities. So again, once we go to simulate the system under normal operations, let's bring the motor online. Now we can see a slower ramp to the soft start, and we should be able to see on plot 2 the effect on my motor. Now, what I could tell, or what I should be checking out, is the per unit change. It's a smaller max for each one of these data points. Does that make sense? So if that means something in my system, and well, here's what's happening in my system. Here's where we start the simulation. 1 second, we're under quiescence. Then we close the breaker, start the motors, activating soft start. run for simulation, 6 seconds. The relay picks up an overcurrent. It gets up to 100% power and then resets the relay at 5% travel, so it didn't trip at all. And then the system got all the way to 100% power. Anybody impressed? And again, we can if we reduce the number of time plots we're calculating, we could take this to a spreadsheet. Now, one other point. So, any questions about that? So, a couple questions. So yeah, that's a simulation of a soft start where we start off at some percentage of full power, and then we're able to change over time how much we're applying. That can be done with a VFD or with reduced voltage or some sort of controller. Now, here's the other thing. So that's the basic function. The activity of the protective devices, like this was a relay that picked up on the current starting overload and then reset. I'll put a fuse here. The question is, what happens to the fuse if we have overcurrent? And this is kind of a neat situation. I'm going to reset. I'm going to fault this bus, in which case we're going to have an arcing fault calculation based upon some device tripping the current. So I've saved that as a script, and if I edit the script, all I've said is run 1 second in normal state, then fault the bus MCC 416, and then run for 2 seconds and see what happens. So let's try to do this. Pick out the script, run it, and what we see is that at the end of the simulation, this bus is offline, and for some period of time, we're plotting bus 2. Let's plot bus 1. So this is the energy that's being consumed during the arc flash. The first trace is the current on that bus into that fault. The second trace is the current in the upstream transformer. And then the fourth is the voltage on the faulting bus. The point I'm trying to make is this is where the electric energy has taken place. And if we look down here, we show our relay MCC4 picked up on overcurrent. The main relay M1 picked up on overcurrent. Utility picked up on overcurrent, or sensed it. The fuse sensed the fault current. The relay here trips first. The relay and has an auxiliary time for the breaker clearing. The breaker on BXTX MCCS above this tripped. The BH main tripped, and the fuse reset at T squared 29%. What I maintain this shows is that my relays protected me, and the fuse as a backup only partially melted. And if we go further, we show that the fuse was reset. So the point I'm trying to make is on any fault, overcurrent fault, we're going to have some amount of fuse protection decreased because this doesn't reset. I mean, it doesn't heal the fuse. So when you have a fault in a system, you need to replace all 3 fuses that are in series with that particular fault, which I find interesting. Okay, so the point being, that we can simulate the real world activity or reaction to most of those simulated models. Can you model a constant current start? Steve, I'm not sure what you're asking. A constant current start. I guess I'd have to go in and model a VFD. That's a good question. Let me take that one offline because I'd have to play with this to see what I could do. But it seems rational. If it's something that you can make a controller do, I think I should be able to program it, at least a simulated soft start. Based on the initial data provided in the stability table, how does the motor starting curve alter in coordination? That pertains to a VFD start, and I didn't include one in this example. It'd be easy enough to go off and do. Let me play with that and get back to you, because it seems to me it would be a good example to demonstrate. And that's, I think, what the tool's made for. So apologies for not having thought ahead on that one. Oh, and here's my motor start torque speed curve I was going to simulate against. And I would digitize this particular curve with the tool rather than import the example. So that's the extent of my presentation. Appreciate the questions. I think I will do a little bit more research on the VFD simulation. I hesitate to anticipate what it's going to say. I'd rather see it for myself. Thank you for joining today. Appreciate your support of EasyPower. Look forward to talking to you down the road. Have a good day.